In this video, I want to discuss kinetic energy, potential energy, and total energy. So you should know that energy is the ability of an object to do work. Okay, and different objects have different abilities to do work. A moving object can do work by crashing into something. Crashing into something will apply a force and move it. All right. A rock on top of a cliff has energy due to gravity. It can fall off the cliff, speed up, and hit something. Okay, a bomb can blow up. That'll create shrapnel that'll hit something and then move it and do work. All right. A spring. Imagine a dart gun where you had a dart in the gun, the compressed spring. The compressed spring, when you press the trigger, the string will expand. That will push the dart out and cause it to have motion, okay? And that can crash into something and do work, all right? So what I want to do is I want to give you a formula for the type of energy associated with motion, gravity, and the spring. And I'm going to mention other examples of work, but I'm just going to mention those and not give you a formula or touch on them too much more than that, okay? So the energy associated with motion, that's called kinetic energy. And the formula for that is 1/2 times the mass of an object times the square of the velocity. Okay? Why does it depend on the mass? Well, if a huge football player crashes into a sofa, it'll move the sofa and apply a bigger force compared to a tiny old lady that's walking and crashes into the sofa. Okay, so clearly the amount of the ability to do work depends on the mass and the velocity, right? You might be wondering why the velocity term is squared. Okay, well, a circular answer is that, well, it's because possibly circular, depending on how you look at it, but it turns out if you change the velocity, that's a much more dramatic increase in the ability to do, dramatic change in the ability to do work than if you change the mass, okay? You could analyze various systems and you would see that it has to depend on the square of the velocity, but let me just give you this anecdote, okay? Suppose that you drove a car at 10 miles per hour and slammed on the brakes, okay? So then you would maybe create skid marks and you could measure the length of those skid marks. Now, suppose you instead were going twice as fast, okay? You slam on the brakes, so instead of 10 miles per hour, you're going 20 miles per hour. How much bigger are your skid marks going to be? You might think that double velocity makes double the length of the skid marks. Not so. Doubling the velocity will quadruple the length of the skid marks. Okay, there's no arguing with that. That's just a fact of life. I don't know if I should recommend you do that, but let's just say that it's true. Take it on faith for now. So doubling the velocity quadruples the length of the skid marks. Okay, so experiments and thinking along those lines led to the discovery that kinetic energy depends on the square of the velocity. Okay, that's all I'm going to say about that. Another example. If you could measure the energy, this gets into another topic which I'll talk about more later, but you could measure the increase in energy by the increase in temperature for some systems. Okay, if you fired a bullet into a glass of water, it would heat it up. If you fired a bullet that was going twice as fast into the same water, it would actually transfer 4 times as much heat. Okay. All right. So now let's talk about the energy associated with springs and gravity and other systems. So the cocked dart gun, the compressed spring, the rock on top of a cliff, a bomb that hasn't gone off, those are all examples that there's nothing really moving yet, right? However, can you see that the loaded dart gun, the rock at top of a cliff, and a bomb, they all have the potential to cause something to move? Okay, so for that reason, we say, well, that's not kinetic energy yet, but it has the potential to have motions. Okay, so that's called potential energy. All right, those examples. And there's multiple flavors of potential energy, so we'll say potential energies. All right. What are some examples of potential energies? And again, they're potential because they have the potential to be converted into kinetic energy, motion energy. All right. Gravitational, a rock on top of a cliff. Spring, okay, the loaded or cocked spring, cocked dart gun, whatever, loaded dart gun, compressed dart gun. A bomb, dynamite, that could be chemical potential energy. Or maybe it's a nuclear bomb, so you have nuclear potential energy. You can also have electrical, okay, and there's lots of other types of potential energies. We can't focus on all of them, so right now I'm just going to give you the formula of the first two, okay? So a rock on top of a cliff, something that has height has gravitational potential energy. Now the amount of work it could do, if it hits you in the head, it's going to be more painful if it's a bigger mass versus a smaller mass. A bigger mass has more of an ability to do work. All right, thinking along those lines, you may be able to eventually come to the conclusion that the formula for the gravitational potential energy is the product of m, the mass, the gravitational acceleration constant, and the height. All right. For the spring, I have to introduce two parameters to explain the spring case. Okay, so when we think about a spring system that has energy, the dart gun is one example. Another example might be, let's say that I fastened a spring to a wall, okay, and then maybe I had a weight hooked up, fastened to the other end, okay, and if I compress the spring and I let it go, it's going to push the box to the right, so it's going to clearly do work, right? The amount of work depends on how much the spring is compressed, and also the type of spring, the stiffness of the spring, okay? The amount that the spring is stretched or compressed, that's a length. That's commonly, let's say that where the spring is most happiest, in other words, where it's at equilibrium, it's not stretched or compressed. Let me mark it with this green dot. Okay, so in the example that I've, and let's say the spring is fastened at the middle of this weight. Okay, so in this example, the spring is stretched to distance x. X is the variable commonly used to describe the distance, the amount that the spring is stretched or compressed from its equilibrium position. Okay, the stiffness of the spring is often denoted by a number called the spring constant, or the K value. Okay, K is a number. So all of that is to prepare you for the formula for spring potential energy, which is 1/2 kx squared. Okay, so we have a formula for gravitational potential energy, spring potential energy, and kinetic energy. Now, the total energy is simply the sum of all the types of energies that are present. Okay, total energy is the sum of all the energy types. All right, so let's finish this video by doing a few examples, shall we? So I'm going to create some hypothetical problems, and we'll calculate different types of energies for these problems, all right? So what is the kinetic energy of a 4 kilogram ball moving through the air at 10 meters per second? Okay, let's think about that one. What is the gravitational potential energy of a 30 kilogram rock at the top of a 20-meter cliff. Okay, and then also, what is the spring potential energy of an object on the end of a spring with a spring constant, let's say 6, and the units are newtons per meter, okay, with a spring constant of 6 newtons times inverse meters, where the spring is compressed 3 centimeters. All right, so let's do these 3 examples. And then also let's do one other example. One more. What is the total energy of a 200 kilogram glider plane at an altitude of 100 meters, moving at a speed of 40 meters per second. Okay, so you can pause the video and attempt these if you like. I'll go ahead and work them out shortly. So the kinetic energy of, what is the kinetic energy of a 4 kilogram ball moving through the air at 10 meters per second? So 1/2 mv squared, 1/2 4 times 10 squared is 200 joules. All right. What is the gravitational potential energy of a 30 kilogram rock at the top of a 20-meter cliff? So the gravitational potential energy formula is mgh. So 30 times 9.8 times 20, which is, let's see, 600 times 9.8, which is approximately 6,000 joules. All right. What is the spring potential energy of an object on the end of a spring with a spring constant 6 newtons per meter, where the spring is compressed 3 centimeters? Okay, so the spring potential energy formula is 1/2 kx squared. That's 1/2 times 6 times 0.03 squared. Now, the reason I had to convert to meters is in SI units. In order to be consistent, we always want to use kilograms, meters, and seconds with the derived units like newtons and joules and other units that we haven't even discussed yet. All right, so let's calculate what that is. So 3 times 10 to the minus 2 squared, 3 times 3 squared times 10 to the minus 4, 27 times 10 to the minus 4 joules. Okay, so, or 0.0027 joules, or finally, my last one I'll do, 2.7 millijoules if you like. Okay? All right, and then the last one, what is the total energy of a 200 kilogram glider plane at an altitude of 100 meters moving at a speed of 40 meters per second? Okay, so what are all the flavors of energy in this example? Well, you have kinetic energy and gravitational potential energy. So the total energy is going to be 1/2 mv squared plus mgh. Okay, and so 1/2 times 200 times 100 squared plus 200 times 9.8 times 40 squared. So that gives, let's see, 100. The first term is 100 cubed, 10 squared cubed, 10 to the 6. That's a million. And then the second one is approximately 2,000 times 1,600. 4 times 4 squared times 10 squared, 16 times 100. Yeah, okay. And so that's 10 to the 6 plus 32 times 10 to the 5. And yeah, so that is, let's see, 1.32 megajoules. 1.32, not 1.36. Okay? So let me fix that. So the reason that I added that example was to show you a total energy example where you had multiple flavors of energy to deal with.